So this has been around for millennia. It's not new, but we've managed to create algorithms that can do this beautifully for us. So, the two cornerstones of ensemble-based machine learning. First one is diversity. First one is diversity. So here the idea is, how can we come up with a strategy that does exactly what I said before? A strategy where each one of the constituent weak classifiers focuses on a different part of the data set. How can we ensure that there is minimal correlation between the weak classifiers? How can we force the weak classifiers to learn different parts of the data set? And then the second one, this is the second key component of ensemble-based learning, is aggregation. So once we have all our weak classifiers and we have an ensemble, do we give everybody equal say in what the final decision is going to be? Do we have a democracy? Or do we have a weighted vote? And if we are going to have a weighted vote, what does that weight depend on? How is it actually derived? How is it calculated? And so how can everything be put together into one? So those are the two key things. If we, particularly this one here, if we don't get this right, then your ensemble is rubbish and it doesn't work. But then if you don't have something intelligent that is able to combine all the weak classifiers, then you're also compromising your ensemble. So that's the heart of ensemble-based machine learning algorithm. So let's do an example. So this is now the very first algorithm, not the very first ensemble-based algorithm, but the first, this was the genesis of boosting. This is the first boosting algorithm that was devised, and from which we have now, we got a platform from which all the other derivatives of boosting were developed, including AdaBoost, which we will cover today. This is how the idea goes. It's a very simple example. So let's say we have our data set. Very simple. We have a binary class problem, pluses and minuses. So we have pluses, these are positive samples, say, something like that. And then we have our negative samples, something like that. So 2 dimensions, 2 features. So what boosting does is, the original algorithm says, okay, let's take a subset. Let's sample this, and let's take a subset out of this and create a sample 1 or data set 1. And let's say we've got something, these 2 samples, maybe that one, and then we've got maybe something like that. What we then do is, with this first sample, we train our first classifier using whatever you like. So we come up with some sort of a decision boundary. So this is going to be our classifier 1, C1. This is what we have now derived from this data set. What we then do is, we take our classifier 1 and we apply it to the original data set. So we take the decision boundary, we plug it into this, and then what we do is we pull out of this original data set another data set. We'll call this S2. Now, S2 is made up of 50% of the samples. 50% of the samples that are misclassified using C1. and the other half are okay, correctly classified. So we might get something like, what might get? Roughly speaking, this is not maybe exact. Maybe something that looks a little bit like that. Who knows? Then we train another classifier on this, and this is going to be C2. And maybe we come up with a decision boundary that goes like this. So now we have two classifiers, C1 and C2. What we then do is we apply C2 onto our original data set, and we take a C1 again, and we apply that to the data set, and we construct a new data set, S3, which is going to be composed of all the samples that C1 and C2 disagree on. Samples that both classifiers disagree on. Right? So one says this is a positive, the other one says no, this is a negative. So we might get something that looks, who knows, something like that. It's very contrived. And so the last classifier is essentially a tiebreaker. It's a tiebreaker. So we train the third one on what is left, and then we have our three classifiers. And then what we do is we take those three classifiers and we apply them to some new data set that we haven't seen before. We apply the first classifier, we apply the second classifier. If both agree, great. If there's disagreement, we apply the third one, and we have a majority vote. It's quite beautiful, isn't it? And this is not as beautiful as it gets. There is a more elegant and beautiful algorithm to come. So the genesis of boosting is here. Now there are very, very strong mathematical proofs that show and demonstrate that this works. This is watertight. It shows that there's an equation there that there's a certain generalization bound. If your best performing classifier has 40% accuracy on a given data set like this, then it shows that your entire classification is going to be much, much better than that. So your overall classification will be better, much better than any of the three. Certainly better than the best one of the three. Right, so that was the mathematical proof that really showed that there was promise in this approach. Real promise.
Sorry, just to make sure I've totally got it.
Yeah.
So if a point has been voted red by 2 of the 3, in the end model it's red?
Sorry, so we're talking about this, we're applying this to this, is that what we're saying? All right, so this one, let's take this example. All right, so we don't know what this is. There's something in here we want to classify. So this one classifies this and says, I think this is a positive. Then we apply this to this, and this one says, I think it's a negative. Then we have to go to this one, and we classify this sample using this, and we go with whatever this one says. So if this one says positive and this one says positive, then we don't really need to ask this one.
But it's done for each individual.
Oh yeah. Of course, so when it comes to actual classification, then we need to classify each instance on its own, right? So each one of these classifiers will take a single sample and its feature vector as input.
So we create C1, C2, and C3 based on same weak class the algorithm. So my question is why C3 we can trust the C3?
Why is it that we can trust C3
when the C1 and the C2 disagree?
Why can we trust it? Well, we can't absolutely trust it. You can never absolutely trust our classifiers. But intuitively, C3 has been trained on samples that both of these have a particular bias against and disagree on. So this one is supposed to, I guess, amplify the grey area where the decision boundary is not well defined. That's the best I can come up with. Because both of these are trying to create a decision boundary, and there's clearly not a clean linear separation. It's clearly something happening in multidimensional space where you're not able to quite tease the classes apart. And then you take the third one that hopefully takes just those problematic samples that are sitting on the decision boundaries, kind of perhaps one is on the other side, perhaps one on the other, and you're looking at it from a different dimension and trying to separate them. So that's why this increases the confidence that the classifier is correct. But it's not always going to be, and we know that in machine learning. Does that kind of make sense? So, look.
Excuse me. Does it only apply to 3 classifiers, or is it?
This works only on 3. The original boosting algorithm is designed for an ensemble of size 3 only. Yeah. And mathematical bounds are proven for this scenario only, in this context.
So which means the C3 is just the C1